In the last few years, a monumental shift has taken place in the field of cosmology, the science of the universe's origin and evolution. Historically, scientists have had a relatively firm understanding of how the universe was formed, primarily based on the Big Bang theory and mathematical models of cosmic expansion. However, some of the latest discoveries, particularly those brought to light by the groundbreaking James Webb Space Telescope, JWST, have shattered many of these long-held assumptions and exposed glaring inconsistencies in our understanding of how the universe began and how it evolved in its earliest stages. At long last, the most advanced space observatory in history, JWST, has unveiled a series of baffling cosmic structures from the very early universe, structures that, according to our previous theories, simply shouldn't exist at all, at least not in the way we expect. The telescope's high-resolution imagery and precision instruments have allowed us to peer deeper into the cosmos than ever before, revealing things that defy our understanding of physics and cosmology. These discoveries are forcing scientists to rethink the very foundations of our models of the universe's birth and early evolution. The most mind-blowing of these revelations concerns the discovery of galaxies and supermassive black holes that should not exist, at least not in their current size, so soon after the Big Bang. According to the prevailing theories of cosmology, galaxies were supposed to be small and relatively simple in the earliest periods of the universe, gradually growing over billions of years as they absorbed surrounding matter, collided with other galaxies, and evolved. But JWST has uncovered galaxies far too massive and well-developed for their supposed age, suggesting that they formed much earlier and faster than expected. In fact, the JWST has already identified 6 enigmatic galaxies that appear to have formed just a couple of 100 million years after the Big Bang. These galaxies are far too large and complex for their age, with some containing hundreds of billions of solar masses. What's even more incredible is that these discoveries have been made from looking at light that has traveled more than 13 billion years to reach us. This means that these massive galaxies were already in place when the universe was only 500 to 700 million years old, an era when our models predicted only the formation of much smaller structures. And it's not just the galaxies themselves that are defying expectations. In the very heart of these galaxies, astronomers have also discovered supermassive black holes of more than 1 billion solar masses. This is particularly perplexing because black holes are not supposed to grow this large so early in the universe's timeline. The implications of these findings are profound. Some scientists are starting to wonder if we are dealing with remnants from a previous universe. Could the early universe be a snapshot of something much older, something that predates the Big Bang? Perhaps what we are seeing is the end of a cosmic cycle, not the beginning. This brings us to a radical new theory, one that is challenging the very foundations of the Big Bang model. The idea that the universe undergoes an eternal cycle of creation, destruction, and rebirth is one that has been gaining traction among cosmologists and physicists. This concept, sometimes referred to as the Big Bounce, proposes that the universe does not have a singular beginning in a Big Bang but instead cycles through endless periods of expansion and contraction. If this is true, then the universe we see today could be just one phase in a never-ending sequence of cosmic cycles. Each cycle might see the birth of new universes, their eventual death, and then a rebirth and a new cycle. It would mean that the universe we live in is not a one-off event but a small part of an infinite, recurring process of cosmic birth and death. The evidence from JWST might be pointing to this eternal cosmic recurrence, where each cycle gives rise to new galaxies, stars, and black holes. But more on that in a moment. Let's first dive into the current state of our models and how the James Webb Space Telescope is challenging them. The expected early universe, a gradual formation. For most of the last century, cosmologists relied on the Big Bang model, which proposes that the universe began from a singularity, a point of infinite density and heat, approximately 13.8 billion years ago. From this point of origin, the universe expanded, cooling over time and allowing matter to form into the galaxies, stars, and structures we see today. According to this model, the early universe was a chaotic, highly energetic place, with galaxies and stars gradually forming as the universe cooled. Early galaxies were expected to be small, dim, and relatively simple compared to what we observe today. over billions of years, they would evolve, grow, and merge, slowly building the more complex galaxies that we see around us in the present day. This model, though constantly refined and tested, has been the cornerstone of our understanding of cosmic evolution. Astronomers believe that in the first few 100 million years after the Big Bang, the universe was filled with a diffuse, hot gas. The earliest galaxies were thought to be small and not particularly massive. They would have taken billions of years to grow into the giant, sprawling galaxies that dominate the cosmos today, like our own Milky Way. But as the James Webb Space Telescope began observing the farthest reaches of the universe, astronomers were stunned to find galaxies far more massive and developed than they could have ever predicted for such a young universe. According to our previous models, these galaxies were supposed to be in their infancy, not already sporting hundreds of billions of stars, each shining brightly in the early universe. Yet JWST was revealing galaxies that were fully formed, and some even appeared to have the kind of mass and structure we would expect from galaxies that are billions of years old. What's more, these galaxies were discovered just 500 to 700 million years after the Big Bang, much earlier than anyone had predicted. The black hole mystery. If the discovery of these massive galaxies wasn't enough to challenge our models, the James Webb Space Telescope also found something even more confounding: supermassive black holes. These cosmic giants, which can weigh billions of times more than our Sun, are supposed to form slowly over billions of years as they accumulate mass from their surroundings. The problem is that in the early universe, there simply wasn't enough matter around for black holes to grow this quickly. Yet, the JWST has found evidence of these enormous black holes at the centers of galaxies that are only a few 100 million years old. Astronomers have long believed that supermassive black holes grow through a process called accretion, where matter from their surroundings is pulled in by their immense gravitational forces. This matter forms a hot, swirling disk around the black hole, known as the accretion disk. In the case of the most massive black holes, those found in quasars, the energy emitted from the accretion disk is so intense that it can outshine the entire galaxy. The radiation produced by this process is thought to be what makes quasars some of the brightest objects in the universe. However, the idea that supermassive black holes could form this quickly in the early universe doesn't sit well with our models. In our current understanding, the formation of such large black holes should take much longer, especially considering the relatively low amount of matter that existed in the early universe. So, how could these supermassive black holes grow to such enormous sizes in such a short time? The most straightforward explanation is that these black holes grew by some other, more efficient method. But what that method might be remains an open question. One possibility is that these black holes were able to form much faster due to the density of matter in the early universe. Some researchers speculate that the matter in the early universe was far denser than current models predict, which could have allowed black holes to accrete matter at a much faster rate. Another theory is that these early black holes formed from the collapse of massive primordial gas clouds, which could have created black holes that were already quite large when they formed. Yet another possibility is that these black holes may have grown in a completely different way than we currently understand. Some theories suggest that the nature of gravity itself may have been different in the early universe, leading to more rapid black hole growth. Whatever the case may be, these discoveries have shattered our understanding of how black holes grow and evolve, particularly in the early stages of the universe. The big quasar question. One of the most intriguing discoveries to come from the James Webb Space Telescope involves the observation of distant quasars. Quasars are powered by the immense gravitational pull of supermassive black holes, and they are some of the brightest objects in the universe. Because they emit so much energy, quasars are detectable even from billions of light years away, making them an invaluable tool for studying the early universe. In January 2023, astronomers used JWST to observe the most distant quasar ever discovered, J12064. This quasar is located in a galaxy that formed just 770 million years after the Big Bang, at a time when the universe was only about 5% of its current age. What the scientists found was both surprising and perplexing. The quasar's central black hole was much larger than expected, around 1 billion solar masses, and yet it appeared to have a fully developed accretion disk and dust ring, just like modern-day quasars. These findings suggest that the black hole and its surrounding structures were already fully developed by this early point in the universe's history, a result that is difficult to reconcile with current theories. The question now is, how did this quasar form so quickly? What allowed its central black hole to grow to such massive proportions in such a short amount of time? And why does its accretion disk look so similar to those found around much older black holes? These questions remain unanswered, but they open the door to a new era of exploration in which our understanding of quasar formation and black hole growth is completely reimagined. The Big Bang or the Big Bounce? Given all these new findings, it's clear that our traditional models of the universe's formation are incomplete. The Big Bang theory, which posits that the universe began from a singularity and expanded outward, has long been the dominant explanation for the origin of the cosmos. But if the early universe was home to galaxies and black holes that formed much earlier and faster than expected, perhaps the Big Bang itself isn't the complete story. Could the universe have originated in some other way? What if the universe goes through cycles of birth, death, and rebirth? This is where the theory of the Big Bounce comes in. Instead of a single Big Bang, the universe may undergo an infinite cycle of contraction and expansion. According to this model, the universe would eventually collapse in on itself, contracting into a singularity, and then bounce back, expanding into a new universe. In this scenario, each cycle would represent a new iteration of the universe, with galaxies, stars, and black holes forming again, over and over, in a never-ending process of cosmic birth and rebirth. The Big Bounce theory avoids some of the major problems with the Big Bang model, such as the singularity at the beginning of time, which violates certain principles of quantum mechanics. If the universe isn't an eternal cycle of expansion and contraction, then the Big Bang may not be the beginning of everything. Instead, it could simply be the most recent phase of an infinitely recurring process. This idea provides an elegant solution to the puzzle of why we're seeing galaxies and black holes that are much older and more developed than our models predicted. Another intriguing possibility is that our universe is the result of a black hole in a previous universe. According to this theory, when a black hole reaches a certain size and density, it can collapse in on itself, forming a new universe. This idea, known as the black hole cosmology theory, proposes that the collapse of a supermassive black hole could create a new universe, with new laws of physics and new structures. If this is true, then our universe might not have begun with the Big Bang, but with the collapse of a black hole from another universe. Wrapping up the cosmic puzzle. Whether the universe is in an eternal cycle of birth and death or whether it was born from the collapse of a black hole in another universe, the discoveries made by the James Webb Space Telescope are forcing us to reconsider everything we thought we knew about the cosmos. For decades, we believed that the universe began from a singularity and slowly expanded, giving rise to the galaxies, stars, and black holes we see today. But with the discovery of massive galaxies, supermassive black holes, and quasars that challenge everything we thought we knew, we may be witnessing a completely different origin story for the universe, one that involves cycles, rebirths, and a far more complex structure than we ever imagined. As more data pours in from JWST, astronomers and cosmologists will continue to wrestle with these new findings. The future of cosmology is incredibly exciting, and we are just beginning to scratch the surface of what is possible. With each new discovery, we move closer to understanding the true nature of the cosmos, our place within it, and the origins of everything we know. The universe is full of surprises, and the best is yet to come.